October 6:30. So I brought the two batteries, the LiFo and the inverter, to Rojas. This inverter has a problem, and it's error code 1. So I'm turning on the battery and turning it on. Makes a lot of noise. And then after self-diagnosing itself, it gives an error 1. So what is this error 1? It turned out to be a stuck fan according to the instruction. I checked it on YouTube. I don't have the actual instruction. The fan rotates. However, when I look at the rotation of each one, this one is slower versus this one. This one is faster. So I checked the frequency of this. And how do you do that? There's connector for the fan. So reference your probe to red and the middle pin. Don't use the black. The black is the control. So it's used to be to throttle the fan. However, at the diagnostic level or self-checking, is actually checking at full speed and check the frequency. Set the multimeter and set it for voltage / hertz and select the hertz. Turn on the unit and check the frequency. Here it's measuring 216 hertz. Which one am I measuring? I'm actually measuring this one, so I'm gonna measure this one. So the other one I'm measuring is saying 13 kilohertz. I don't think it should be 13 kilohertz. However, the speed of the fan is not 13 kilohertz. So motor can't run at 13 kilohertz. Multiply that by 60 will give you the RPM. It's not giving you that RPM. So these are what you call brushless, and there's a Hall sensor in here, and it would give you it would sense the rotation of the fan, so then it pulses out and detected by the computer. So now let's see. If I replace this, I think this is the problem. We'll see what happens. So I've taken out the bad one and replaced it with another fan. So we're going to see what's going to happen. I think this is the failed fan. They don't last long. I don't know how long this inverter is. A year, I think. So I would suggest that if this thing fails, then add a quick disconnect here so that they can be easily replaced without having to finagle the connector out of there. It's kind of difficult. So we'll test it now. So I'll turn it on. So no error code. So we fixed the inverter by replacing this fan with a different fan. I'm going to check what this is from Lazada and have spares just in case, well, for future, because it will fail again. Okay, it's all set up. I'm going to run up the cable to the roof. This is the cable, and I'm going to start using this soon. I'm going to have fun a minute with this setup again. October 24 noon. With the typhoon here there's not much to do, so I've decided to tackle this inverter with error code 09. Before doing anything, one should take a picture of where things are connected, because once they're disconnected, you gotta know where things are going to be. So it's important to understand where things are supposed to be connected, because the pins look similar, maybe different, similar. So one has to be mindful of how the connections are inserted. So here the circuit board is taken off the housing. So I'm gonna flip it over and check the back. Or I'm just gonna do a quick visualization of, or visual check of the components. So looking at this component, it released the silicon. It made a smoke emitting diode or smoke emitting component. Don't know if these are damaged. These two are baked, cracked. This two looks to be damaged. Probably all of them are damaged. Hopefully these are not damaged, because are there any marking on these things? I can't see marking. Hopefully they're okay. Looking at the component on this side, I don't see anything damaged. I'm gonna take the flashlight. There's a bunch of fuses here, automotive fuse. I'll have to check each one of those fuses. Okay, using a flashlight to look at the component here, this seems to be okay. So it looks like these are the one that's basically fried. The heat sinks are removed, so these are now exposed to be taken apart. Now, when these fails, do not try to save what you think to be working components. It's a waste of time. Just get at it. Replace all 8. Just because 2 are good doesn't mean that they're good. Because these 2 fails, it means that these 2 will fail also. Similarly these. So don't try to figure out whether they're still working. Don't waste your time. Just replace them all 8. And I've noticed people working on this kind of circuit board, they're desoldering the components. Well, never mind that. Just remove the components and then afterwards get at the leads. The components are badly damaged. This is what it looked like close up. I mean, that's overcurrent right here. It released the magic genie inside the component. So the component that's damaged is George 042 Nancy 10. So I'm gonna see about where to get this part from. Probably from Lazada. So when you're looking for the component at Lazada, look for G042N10. It's around 330 peso for 5 pieces. So 5 pieces is 320 peso. Now I need 8. So 5 pieces. So basically 600, 700 peso, not including shipping. So I'm going to order today, so that'll come in the next few days. When working with circuit board and you need to desolder components, it's important to have a tool that you can control, set the temperature correctly. You want the tip to get fairly hot because these circuit board have quite thick traces, and the traces will act like a heat sink. So you want to place the tip there, and right away in seconds the solder begins to melt, and then pull off the pins like this while it's hot. So I'll do that. So these are the leads that were pulled off the circuit boards. It's a lot easier to remove the component and then remove the leads after. I notice a lot of people save the components. I don't get it. They're already damaged. Why work hard to remove it whole? It's useless. Get at it. Remove the body, and then what's left is the leads, and then it's easier to remove the component after. Okay, the holes are cleaned. You gotta know the right way to do these things, otherwise the pads will lift, and then you gotta do jumper. So that's based on years and years of working on circuit board. Eventually you'll get the feel of the temperature of the pads. For example, if the pads are tied to copper core, you want to make sure you have the right temperature, otherwise that thing is hard to desolder. So this cleaning the hole took me like 5 minutes. It's fairly quick. So I did a brief reverse engineering of this circuit board. So the negative is common to all of the source or drain of the MOSFET. And what's being switched is the plus through the fuse, and then one leg of the transformer, and then are separated into two branches. One leg here is separated into two. So I did the reverse engineering of the circuit board. This is ground, battery. So this copper core is ground. And this is the plus. Again, copper core, fuse is here. And then this is switched by these two coils. So there's a common coil here. This goes to this branch of the coil, and this goes to the branch of the coil. So this is plus, so it's pulse switching. Okay, it's up converting the DC into pulsating DC, and this is the output. And then the output is driven by these MOSFET. So someday, well, I mean, I can reverse engineer this thing. Is there a brain to this guy? Actually, is there a brain? Oh yeah, there's a brain. Wonder what is the brain. Anyway. So it's quite simple. So the 24 volts is boosted, and then the boosted volts are then switched by these I guess IGBT something. I wonder what this is. Let me just. So these are multiple array of diodes here. So kind of makes sense. And then the IGBT or MOSFET then drives the other transformer here. No, this one. Actually, no. Probably. I guess I have to reverse engineer this thing. Anyway, this will then through this relay gives you the 220 volts. I wonder if this is involved. Let me just do a quick check. So this transformer is not part of the output voltage. It takes incoming 220 volts, and then actually I don't know what it does to really understand what this is used for. I guess it probably help in paralleling the output voltage somehow between 220 and then battery. These two works in conjunction. Anyway, so these components drives this transformer, which gives you the output boost, which then are driven by the IGBT to give you 220 volts. This is what I think is happening. To fully understand the circuit, I gotta reverse engineer it, and not interested in doing that because I'm not manufacturing it. So what's the point? I just want to fix it. Anyway, this is end of part 1. Stay tuned for part 2. So I'm looking at the pins. So here, G for gate, S for source. So the middle pin is drain. So it's similar to the other ones too. And because they're the same component, so source, drain, gate. These are the driver for the MOSFET. So I'll just do a quick check on the circuit. Mental reverse engineering. So this component is 2 SAM alpha 1020L, while the other one is, and this one is 2 SAM Charlie 2655. So I think they're NPN, I think. Anyway, they're probably similar to this, since they're mirror image, so they're probably this. So I took a look at the micro. It's actually formerly Motorola. Anyway, now it's called Freescale. It's MC9S08 or MC9S08A060. That means that it has 60K of ROM. And this is the BDM connector to communicate to the micro. I can actually reverse engineer the firmware if I wanted to by reading the code. In fact, if I wanted to, I could remanufacture this circuit board. Waste of time. Can't manufacture anything like this in the Philippines. November 3, 9 o'clock. So the parts came from Lazada. So there's 5 and 5. With these two, it cost 600 shipped. So now I did check the resistors, and I'm using this as a reference because it's not populated. However, there's something wrong with these values. Anyway, with these 4 populated MOSFET in channel, the resistors are cooked, damaged. So all of them are damaged. There's 2 here that's not damaged. However, mostly all of them are damaged. So I did some simple reverse engineering of how this thing works and how the MOSFET and driver with these NPN and PNP, and a little bit of how this circuit works. However, I'm mostly focusing on how this system works on this side. The placement of the resistor is way too close to the MOSFET. When the MOSFETs get quite hot, the heat conducts toward the resistors, and eventually the resistors will be in that state where it really doesn't do its job because it's way too hot. And when the resistor gets too hot, whatever power rating it has initially will disappear or impacted or derated, so that they will now be easily damaged. What the designer should have done is move it away a little bit from the influence of thermal runaway, or use a higher rated resistors like these are, let's see, with these components, I think they're rated at 0.25 watts. I can't remember, or 0.125 watts. And so, and then when it gets fairly hot, it just loses its property. So that's why they're easily damaged. And I don't know, the designer basically, quite honestly, this thing is designed to be obsolete, and these are hard to repair. So basically, one is forced to buy a new one if this thing can be repaired. The with this type of damage, the pads on the component will start to lift or lifted already. So sadly, when I will replace the component, the pads will probably lift, and now I will have to do jumper them to make it work again. I was thinking of replacing the resistor to be higher rating. However, it's not possible because the component's way too small. So I briefly spent several minutes reverse engineering the circuit board for the fun of it. I needed to understand how the NFET or MOSFET N channel are driven. So basically, this is the driver U1. Through this drives the MOSFETs. This chip drives the FET driver, and this receives the signal from the isolator, opto isolator, then the micro. So there's a bit of a isolation of the low voltage, and the designer decided to isolate certain part of the circuit just because it's. If I was designing an inverter, I'd probably do the same thing, learn a little bit more about it. So this is the schematic that I drew up of the inverter, and this transformer is with the middle pin. It's driven by MOSFETs. This is the MOSFET driver through these PNP and NPN transistor. And basically, like I mentioned before, the drain, this is drain, and it pulses the transformer using the battery as the middle pin. So this thing is pulsing, and this part is pulsing also. So it's a mirror image of the circuit board or the circuits. So this TC4427 is microchip KA3525. I don't know. I've forgotten what it is. So these transistors are fried when these overheat. So this R6 limit the pulse current driving the gate of the MOSFET, and these are the pull down to quickly discharge the gate capacitance. So when these gets pretty hot, because these two components are pretty close to the component, they get fried, they burn up, they pop. So that's the reason why this design, they did some validation. However, they didn't really fix the thermal characteristics of the component. They just allow these two components to fry. Basically, built-in obsolescence. They could increase the rating of this component. However, just basically says, well, it is what it is. It'll just fail. So this key A3525, basically this is obsolete. So this inverter might be unable to be repaired in the future. So are these. So when I look at the inverter, there's quite a bit of obsolete part, or not to use for new design. So this is this is basically what the inverter look like. This gets fried from overcurrent. The component gets fried from thermals, and basically because it's switching this side and switching the other side, they all will be fried. So now I don't know if these components are fried. So now I have to buy these component, the resistors, so that I can repair the circuit board. So where I thought I would just replace the MOSFET, it turned out now I have to replace the resistors. I don't know what else to replace. I suppose one thing at a time, replace this and then see what happens. So that's what it is. Yeah. Oh well, this is life. November 27, 11:30. So the parts from Lazada arrived, the 30 ohm and the 8, 10, 20 transistor arrived. So I am going to install them here, remove the old ones and install the new ones. Okay, the 30 ohms are installed, and when you get to that age where you can't see the components, it's really hard to install. So it took me a while. I've also replaced the 8, 10, 20. So all of these components are replaced. The NPN, PNP, and all of the resistors are replaced. The damaged ones, whether they're good or bad, they really need to be replaced because really you don't really know whether they actually are good. So you might as well automatically replace them. No point in reworking that circuit board, especially once you have to take it apart. I've added thermal paste to the back of the component. That would help speed up the heat transfer to the heatsink. So I installed all of the MOSFETs and I turned it on, and it blew the fuse. So it means that this thing has additional problem. So I took out the transformer, and the desoldering this component is really tough. You really have to have the iron set at max, to the point where the iron tip is turning blue due to heat, overheating. So I overheated the iron tip, because if you don't, this thing would be hard to desolder. So I did that. I mean, when you do that with soldering iron where you overheat them, they don't last long. And when removing this component, it removed this plating through, or plate through copper. So as a consequence, it sort of reduces the contact to the circuit board. Oh well, that's how it is. So really, to do this, you really have to have yeah, well, you gotta have the proper tool. I mean, you just don't do it for the fun of it. I did it because it's not working. So what are you gonna do? Learn something from it, or it's going to be it's gonna be bricked. It's just basically a doorstop. So anyway, I'm now going to power it up and then see the signal happening. I need to add a pull up or a pull down, whatever, because without this bridging the 24 volts, then it's kind of hard to diagnose the circuit board fault mode. So I powered it up and checked the gate. So both sides are driven high with 5 volts. So I'm not sure why. Well, I'm kind of sure. With both sides turning on, it's gonna draw a lot of current. It's not pulsating. So I don't understand why it's not. So I'm just gonna look into the reason why. It's possible that this component is no longer working properly. It's a buffer. It buffers, well, it's a driver for these transistors, so they should be acting like buffers. However, it's there it because both sides are on. Most likely that this is damaged. What I'm going to do is remove this component and then see how these two sides behave. So when I took out this component, the gate voltage dropped to 0. So I suspect this thing was fried. Basically, I think these failed, and so they impacted the output of this MOSFET driver. I won't know for sure until I buy a replacement for this component. Then I'll see. December 14, the MOSFET driver TC4427 arrived a few days ago. So I'm going to install it into the circuit board. 10 pieces, and it cost 571 for 10 pieces. So divide that by 10. So let's just call it 60 pesos. So it's $1.50 per component, dollars, around there. So this is, I think, microchip. So I'm just gonna check if it is microchip. So it's from microchip. When I was checking out other components like these, there are other components. I don't know these other suppliers or maker of chips. However, I'm familiar with microchips since I used them quite a bit in the past. So now I'm just gonna solder this component into the circuit board, onto the mic. Soldering so one has to use these tips. Since I want to solder the individual pin onto the into those pads, having a thicker tip, it would be difficult, prone to bridging. So I'm gonna use this first, and then if it doesn't work, I'll use a different type of tips. Okay, I've soldered it. It's been a while that I soldered Suwick. So this, in the past, there would have been 5-minute works. Now it took me 15 minutes, 3 times the time to do these things. So yeah, age does these things in practice. So I haven't practiced for 7 years. So now Everything I do with components, it takes me 3 times the amount of time to do things. Okay, when I replaced the TC4427, I checked the gates, and it seems like they're doing what they're doing. It appears that they're pulsating. However, because I don't know for sure, I'm going to use a scope to scope out the MOSFETs, gate driver. To turn on the circuit board, I use a jumper, and just jumper this 2 pins. Okay. So, as one can see, it's pulsating. Let's see what the frequency is. Let's see, down. Okay, so this is how the MOSFETs are driven. So it looked like, in summary, I replaced all of the damaged surface mount resistor, replace these NPN PNP components, and then replace the SOEC. Now it's working. So in theory, this inverter is fixed, but I don't know yet until I install the transformer back. So far so good. So after replacing all of the component on this side, and I put it together using this battery, I turn it on, and once it energized the output voltage, it blew the fuse. So it means that this side has a problem, and quite frankly, I'm losing my interest in having it have this thing fixed, because now I have to disassemble this, look for the problem. Probably several MOSFET is no good anymore, so I'm debating whether I have the interest to have this, to fix this thing. So I think I'll leave it alone until I gain my interest in fixing this thing. So MOSFETs and other components are replaced. I checked the output waveform, and it looked to be normal. Now when I turn it on, when it begins to drive the output voltage, it blows the fuse on the battery. So this means this side of the driver is no good. So why is it no good? So this kind of frustrating. Well, since I have nothing to do, I've decided to tackle this circuit board. I'm going to desolder all of this because it's the easiest thing to do, I think. I mean, goodness sake, this really sucks. Wow. Let's see here, we have the bridge, some component bridge. No, that's the bridge. Anyway, I decided to tackle this thing and desolder the whole thing. Here's Minute, my cat. So I lifted the whole thing. Sadly, some pads lifted, and it happens when the solder is not taken out completely, or enough that it doesn't adhere to the pads. So most likely I probably have to do a jumper. Anyway, sad. That took a while. It's a lot of pins. So now I'm going to check which one failed. Actually, I have to see whether I can buy them at Lazada or elsewhere. So these two components are no good. They are, what are they? 640T60M. Too dark to see. It's not a Zik, it's a G. Now, because these two are damaged, so it's probably one leg of the bridge, each bridge. So it probably created a shoot through and destroyed these two components. The thing is, with these driving the I have to reverse engineer this. It's probably driving this inductor for the 220 volts output. So yeah, otherwise these are good. However, because I did this is a diode. I will have to replace the leg, because actually no, the legs is fine, bridge is fine, this too is fine. So these two are the component that failed. I don't know. I don't even know if these components are okay. Components is 4992. I have to check. 4992. Okay. Well, gotta check the all of the surface mount resistor and see what happened. December 28, 9 o'clock. So I bought these IGBTs from Lazada. I actually ordered different part number. This one here is the proper part number, G40T60AK3HD. This one is G50, and this one is G75. So with the G40, I think it is G40, the continuous current is 40 amps with pulse current to be 80. This one being 50 amps continuous with a pulse current of 100 amps. And this one is 75 with a pulse current of 150 amps. So when you're looking at these, you have to look at the parameters. One of them is charge at the gate and the nanocoulombs. With the G40, it's closer to G50, so I decided to use G50 instead of a G75, because the nanocoulombs for this, it goes up to 300 something, and the charge is quite high. So what does that mean? It's when the device is being turned off, the higher the charge in nanocoulombs, the longer it takes to turn off. And if you don't have the proper off time, on time, it will create a shoot through. So I'm just going to when repairing these, you have to replace all four, not just because of the damaged ones. It's basically they are already impacted, so replace all four, not the one that are damaged. Putting back the component with all of these mini pins is kind of hard, so you gotta have patience. One has to develop patience. It really is difficult. One has to make sure all of the holes are clear, otherwise it's hard for the pins to protrude out. They actually will bend out of the way, so I had to remove this array several times before all of the pins lined up. So now I'm going to solder these. However, before you do anything, one should do a what you call sanity check. Make sure all of the pins have protruded, because once you start soldering and you have to desolder them out again, it's a pain. So better to do sanity check before having to solder the pins. So everything is put back together, so I'm just going to connect the inverter to the battery and turn it on and see what happens. So everything is connected, the fuses has been replaced, and I'm gonna turn it on. So far so good. So there's actually an output now. So we're going to see the output voltage. So this is the output. I'm gonna put a meter on it. Okay, let's summarize the failure mode. So why did this MOSFET here burn? It's because the IGBT is shorted, and so it put a great stress to the MOSFET, because what it does is it pulses this transformer to give out 220 or 240 output, and when the load out of the transformer is great, it overheats the MOSFET, and not just the MOSFET, it would overheat the resistor, transistor, and the driver. So basically, the bridge here, the IGBT bridge, is damaged by a shoot through. It overloads the transformer, and the MOSFET tries to drive the transformer, and they couldn't handle the overheat, and it would just get burnt. They go thermal. So it's a cascading effect. Damaged IGBT cascades back into the 24 to 220 volts transformer. Overheat. There's probably a rapid thermal, and the computer is unable to manage that. In theory, it should turn off the system before any failure will occur. However, the rapid failure is that the computer itself cannot handle it, so it'll keep driving the MOSFET, and eventually the MOSFET fails. So that's how it works. It's just a cascading of failures. So number one, shoot through, damage the IGBT. Number two, the MOSFET will keep pushing current through the transformer. Eventually the MOSFET will goes thermal. It takes along with it the 30 ohm and the 20K ohm pull down, and then the NPN and PNP transistor, and then the driver. So from this lessons learned, you don't actually need to create a schematic. As long as you understand how the MOSFET drive this, and how the IGBT bridge works. No schematic required. You can fix this kind of stuff by experience, by tearing down something like this and then figuring out what needs to be replaced, and so on and so forth. So if you're asking for schematic, the schematic is in my head. I'm too lazy to create a full schematic of this circuit board, so don't ask for it. Simply that it's really easy to repair this kind of stuff. What goes wrong? IGBT bridge, MOSFETs gets damaged, along with the associated component, resistor, and driver. As long as the computer is working, you can repair these quite easily. So that's it. So honestly, if having now repaired this and looking at the time I spent on it, piece-wise, aggregated, it's less than an hour. You just call it an hour. What's the longest time is the waiting to procure the component from Lazada, if you can get it. That's pretty much it. It's really quite simple to fix this kind of stuff. Keep in mind though, when I was looking at the data sheet of the component, they're obsolete. Even this Freescale or NXP computer is getting up to being obsolete. So basically, once a component, you can't buy the component. Like this micro 9S08, 9S08. I've used 9S08 for many years, and they're getting up to the obsolete. They're probably obsolete by now. They're probably going to go last buy, something like that. And that's pretty much it. Simple, easy peasy. Thanks for watching.